In the previous examples, we talked about using the z-test statistics for hypothesis testing when sigma is known. So this is the formula that we used actually in chapter 8 for the previous chapter and for the questions that we did earlier about when sigma is known. But now we will be moving and talk about when sigma is unknown. In chapter 8, we introduced situations in which the objective was to estimate a population mean when we did not know the population standard deviation. In these cases, we use the critical values as a t value, not the z value. We use the t value from the t distribution rather than the z value from the standard normal distribution. So the same logic, we're going to use the hypothesis testing when sigma is unknown, as we did in the chapter 8, right? When sigma is unknown, we're going to use this t value, the t test. This is the way that we're going to find it. And we have a small assumption, as we did before. We will be assuming that the population is normally distributed. And the degree of freedom is going to be n-1. The degree of freedom is n-1. So let's go to an example. The dairy fresh ice cream plant uses a filling machine for 64 ounces cartons. There is some variation in the actual amount of ice cream that goes into the cartoon. The machine can go out of adjustment and put a mean amount either less or more than 64 ounces in the cartons. So basically, the boxes have to contain 64 ounces, right? Other than if the box is out of the adjustment, it will be greater than or less than this amount. And they are taken, so to do this, to monitor the process, the production manager takes 16 filled ice cream cartons each day, and he assumes the assumption is met. He assumes the population is approximately normal. This is important to be met before we start doing the hypothesis testing. Because the standard deviation is not known for the population, the data is given to us, and the significance level used is 0.05, so this is our alpha. And we are given the sample data. He collected sample of 16, and he wants to conduct the hypothesis testing. Because we don't know the standard deviation, we know the S, basically. We can know the sample standard deviation S, okay? So the sample standard deviation, and we also can get the X-bar test from here. We can get the X-bar of the sample, which is the X-bar test. So let's do this. Let's find the mean and standard deviation from Excel. Average. And standard deviation, this is sample, remember, std.s. So this is approximately 0.72. And the mean is 64.2. So 64.2, and the standard deviation 0.72 s for the sample, okay? For the sample. Now let's go to what's so called the Minitab. By the way, let me copy this and go to Minitab as well to show you something. Okay, stat. Basic statistics. One sample t distribution. We have one sample t. Now, we can do this. Either we can use this, one or more samples each in a column, or we can use summarized data. Summarized data, we have the sample size, we have sample mean, we have the standard deviation of the mean, but because I have the raw data, I can use it. Okay, if you don't have the raw data, you can use the other one. Make sense? I can place 16, sample mean is 64.2, sample standard deviation is 0.72, perform hypothesis testing, hypothesized mean 64, options. Let's do both of them, by the way. Maybe you have small minor things. So the data is here. Hypothesized mean is 64 ounces. Perform hypothesis testing, yes. Make sure that this is checked. Confidence level 1 minus significance level 1 minus alpha, which is 95%. Alternative hypothesis when the mean is not equal to the hypothesized mean. Equal. Right? So what is the t value? The t value. Now we don't have the z here, we have the t test. T critical. T critical here, T critical. What is the T test? 0.95. What is the P value? 0.36, right? Okay, I just updated the data. I have a mistake in one of the data. So anyway, I just updated the data. The nice thing about the Minitab, if you update your data, you can update the result without redoing everything. For example, if you add, let's say, 65 here, suppose that I'm adding 65, then it asks you update these results, create new results. If you click on update, then it will be updated. So let me delete this. Now, delete. So now we have this. So let me just change the value we got. The p-value is 0.2, sorry, 0.27. And the t-value is 1.15. Okay. So to do the p-value with the second method, p-value with the alpha, p-value is greater than alpha. So that means the area is greater than the area, or the p-value is, the area is greater than the alpha. So that means we fail to reject. We are not in the rejection region. We fail to reject the null hypothesis. We fail to reject this fact. We fail to reject this fact. So we don't have sufficient evidence to support the alternative hypothesis. We don't have any evidence to support that the machines are out of control or out of calibration, right? So, or out of adjustment. So we don't have sufficient evidence to support this claim. To do the T critical, again, to do the T critical, we just go to the graph, probability distribution. We choose T test. Degree of freedom is n minus 1, n 16, minus 1 is 15. Okay, n is the sample size. Now, right tail, left tail, equal tails. We have equal tails. What is the probability of the equal tails? 5%, because we have two-tail test. Again, this is a two-tail test. So what the value we got? It's 2.13. So the T critical is what? 2.131 or negative 2.131. So the 1.15, the T test, oops. The t-test is 1.15. 1.15 is less than 2.1, and it's greater than negative 2.1. It's here, basically. That's why it's not in the rejection region. The t-value, the t-test value is not in the rejection region. It's not within the cutoff value. It's not in each of the cutoff region. It's outside. It's outside, right?